Hello, Durham. My name's Jay, and this is my poster on the elastic production of top quarks. So what makes a process elastic? When protons interact, they usually don't survive and break apart into proton remnants, especially when making objects as heavy as TT bar pairs. However, on rare occasions, it is possible that one or both of the protons survive the interaction. There are therefore three kinds of events: inelastic events where neither proton survives, semi-elastic events where only one proton survives, and elastic events where both protons survive the interaction. For events to be elastic, the mediators of the interaction have to have no electric or color charge. And there are only two kinds of particle that can do this: the very familiar and common photon, and the extremely unfamiliar and very weird pomeron. Pomerons aren't real particles, but they're a useful effective particle to describe elastic interactions. They're a type of Reggie trajectory, but to explain them properly we'd have to open a whole Pandora's box of weird 1960s physics, which we are not going to get into today. Just think of pomerons as ripples in the strong force. So, we can have photons being the mediator, pomerons being the mediator, or even a mix of both. And if we include the semi-elastic cases as well, we have 5 processes that all contribute to elastic top production. So, why haven't we observed this process already? Well, the cross-sections of these processes are quite small compared to inelastic TT bar production. It would be very difficult to spot the rare elastic cases in the data, but there is a trick we can use to almost completely suppress the inelastic case. When protons interact elastically, they lose some energy compared to those that don't. The LHC needs to maintain a consistent beam energy, so magnets sweep out these lower energy protons, where the angle with which they're deflected from the beam being directly proportional to the amount of energy they've lost. Both ATLAS and CMS exploit this effect by placing dedicated forward proton detectors down the beam line, away from the central detector. These proton tags only exist when a proton is interacted elastically, so all we need to do is look for a TT bar event in the central detector and a simultaneous forward proton tag. Can it be that simple? Well, no. At least not in normal data-taking conditions. As always, the problem is pileup. In normal data-taking, dozens of other interactions happen simultaneously, including elastic interactions. And though the central ATLAS and CMS detectors are very good at removing this noise, the forward detectors can only say that a forward proton was detected, not where it came from. But the LHC does occasionally perform special runs with very low pileup, mostly to help with measurements of the W mass. So can we use this data to measure elastic top production? To answer this question, we need to know how much data we'll need for an observation. And for that, we require several ingredients: the cross-section of the process, the acceptance of the central detector, the acceptance of the forward detectors, the survival probability of the proton, more on that in a moment, and the number of events we need for an observation. The simplest of these is the number of events. For discovery, the bare minimum for a 5 sigma counting experiment is 25 events, but let's say 100 to be on the safe side with systematic uncertainties. The cross-section of the process we can take directly from Monte Carlo. There is no single generator that can simulate all of the processes we want: elastic pomeron-pomeron, photon-photon, photon-pomeron, and semi-elastic pomeron or photon production. Pythia can do most, but not all. MadGraph can do anything with photons, but not pomerons. Herwig can possibly do everything, but the authors haven't confirmed that, so we're not including it here. And there are 2 dedicated generators that can handle only the fully elastic case: Superchick and FPMC. For the semi-elastic cases, the cross-sections are quite high, on the order of a picobarn, whereas for the elastic cases, they're on the order of femtobarns. But this is missing a crucial part of the story. When protons interact elastically, there is still a chance that they can continue to interact and break apart. This is called the proton survival probability, and it has either a small or huge impact on the cross-section, depending on the interaction mediator. Photon interactions can be quite long range, and therefore, the likelihood that the protons continue to interact is small. At low MTT bar, this is as high as 80%, and drops to 50% at high MTT bar. Pomerons, however, are a QCD interaction, sort of, and therefore are very short distance interactions. The protons are highly likely to keep interacting in this case, destabilizing the proton and resulting in a survival probability of just 3%. If we apply these survival factors to the cross-sections, we see that the pomeron processes now become much lower, dropping by 2 orders of magnitude. Okay, so now we have our number of events and our cross-sections. What about the detector acceptances? For the central detector, I'm prototyping the acceptance based on ATLAS, just because, firstly, I'm an ATLAS member, though this isn't an ATLAS poster, and also because Atlas has lots of publicly available information on its acceptances. We don't have the luxury of focusing on just the leptonic TT bar channels, so we need to consider all decay modes, even the ones including taus, as well as slightly looser than normal selections. But remember, this is low pileup data, so we're perfectly allowed to do this. We end up with an acceptance of 2% for the dilepton channel, 20% for the lepton plus jets channel, and 5% for the all-hadronic channel. For the forward detectors, we can use some public data and our Monte Carlo to model our forward proton acceptance based on their PT and their relative momentum loss. We find that the acceptance of Pomeron processes is around 20% and photon processes is around 30%. It's worth pointing out that the limiting factors for these acceptances aren't really the detectors themselves, but rather the position of the collimators, which block protons from reaching the detector. Now that we have all our ingredients, we can work out how much integrated luminosity we need to detect these processes. To obtain just 25 events, we'd need this much data, and to obtain 100 events, we'd need this much. These are perfectly manageable numbers. In fact, the LHC has already delivered this much low pileup integrated luminosity during Run 2, though the forward detectors from Atlas and CMS were not always online to collect it. In Run 3, it is easy to imagine that we could get this much data and observe these processes for the first time, and perhaps we can get evidence for them in the existing Run 2 data.